Okay, can you see this book?
Yes, sir.
Okay, good. Okay, yesterday, not yesterday, last week, yeah. Last week, we have discussed about Faraday's law. Faraday's law is basically about this magnetic induction that occurs the electric induction, okay? This is so because we have the flux, the magnetic flux depends on time. So this is the laws induction, Faraday's law of induction. Okay. This epsilon is this electromotive force in the induced electromotive force, yeah, like the source of the voltage, okay, that caused by the change of the flux, the magnetic flux with respect to time, okay. This minus, it means that this induction, this electric induction is opposite to the magnetic, the original magnetic field, yeah, okay, somehow against the magnetic field. I will explain it later. Okay, this phi b is the magnetic flux. This is phi b. It means that this integral b dot dA. Okay, because this is the product scalar. It means that we have BA cos theta. This theta is the angle between the normal vector of the surface and the magnetic field. Okay, so this is the picture left in the figure, the 31.3. Okay, so the application of this induced electric field, you see that this is from guitar, yeah, electric guitar, which amplify this sound of the amplified guitar using electric induction. Okay. Okay. So this is electromotive force, this induced. Okay, let us consider, for example, this figure. Okay, because for example, this road, yeah, in microscopic point of view, this should be, there is an electron here. Okay, this electrons goes to this to down, yeah, downward. Okay, this FB here, and this what is it called? This electric force, yeah, up to the up. Okay, so if this, for example, becomes equilibrium, so it should be this the electric force, yeah, equals to the magnetic force. So we get this E equals V times B. Okay. So the equilibrium means that the electrons have constant velocity or constant drift velocity. Okay. So if the electron goes downward, so it should be the current. The current should be upward. Yeah, okay. From down to up means upwards. Okay. So, for example, if we have resistance and we have this a loop here, then there is a conducting wire or conducting rod, and we apply the conducting rod. Yeah, we pull the conducting rod with the velocity v. So in general, v is depend on time, but there is a time when the acting force, the external force, okay, getting becomes equal to the force caused by the magnetic field, which is from the induced magnetic field. Okay. So because the flux becomes bigger and bigger, so it should be there is induced magnetic field, which is B in here, which caused by the current, the induced current. Okay, so the induced current here is for, counterclockwise. Okay, this counterclockwise. Okay, so because the potential difference is E times L, okay, if we use this above equation, then we get this potential difference between at the road, yeah, is equal to BL times V, okay. So in general, this equation coming from that this applied force on the roads, yeah, becomes equal to this magnetic force. Okay. So if the force or the rod in equilibrium, it means it is at rest or move at constant velocity. Okay, so V it could be a constant, this final or terminal velocity. So this terminal, it means that we have a constant velocity. Is there any question? So what happened? This is we pull to the right, okay? If we push to the left, what happened?
I think the FB would be to the right.
Yeah. Sorry. What the? Can you say again?
I think the FB would be to the right.
Okay, FB could be the right. Okay, and what about the direction of this current?
It counters the direction before.
Okay, so the direction of this current should be clockwise. Okay.
Yes, sir.
Yeah. So this second figure, it means that the above figure, this figure A equivalent, we can say that we have a closed loop, yeah, with the current I and this resistance R, and we have this, let's say this induced or motion electric EMF, electromotive force. Yeah. This the battery we could thought of as the battery, this rod, okay, whose the potential difference, the magnitude of potential difference is BLV. Okay. So you could also this formulation is should be, for example, VB equal BLX. X is this one. Okay. Because X depend on time. Yeah, so it should be this be the X here. This should be minus BLX, okay? This is a minus because we have somehow this EMF is against the magnetic field, okay? So we get this one. What about the power that delivered by the applied force? So we get this, for example, this power is equal to the F, this applied force, times V, okay? Because this applied force is equal to ILB, so we get this ILB V, okay? Then we insert this I from 31.6, we get this equation, okay? Somehow this dissipative power, yeah, dissipative power at the resistance. Is there any question? Any question? No. Okay. Let's see. So, for example, this motional EMF induced in a rotating bar. I think, yeah, I should give it to you. Let's say consider a rotating bar of length L rotates with a constant angular speed omega about a pivot at one end. So it rotate around this point, yeah, O, this center. Okay, and it moves, it rotates in the uniform magnetic field B directed to the perpendicular to the plane of the rotation. Okay, as shown figure, find the motional EMF induced between the ends of the rod. Okay, between this end. Okay, so we get the flux. Okay, the flux is dV/dr, okay? This dr is the infinitesimal element of the rod, okay? Because B is a constant, okay? B is a constant. Oh yes, I forgot. This V here is equal to omega times R, okay? Because omega is constant, so we could take together with B out of the integral, and then we get this one. This is the induced potential difference, or induced electromotive force, or EMF, at the rod. Okay. So this is already, I think. Okay, let us consider this way. This problem. The conducting bar is rated by 3112. Moves to frictionless bar parallel rails, yeah, in the presence of a uniform magnetic field directed into the page. Okay. The bar has the mass m and its length L. The bar is given the velocity vi to the right and is released at t equal to 0. So using the Newton's law of motion, find the velocity of the bar as the function of time. Okay, so number A here, if you see that this F equals to this applied force here, F, this one. Oh, sorry, this, so this bar moves directly from this VI, okay, to the right, okay, without we we pull or we push, yeah, without external force. Okay, external force maybe only this FB. So if we get from the picture here, because there is no applied force as the previous example, we have this Fx equal to Ma, this equal to Fb, okay? This Fb is minus ILB, this one, this Fb. So if you compute this V, this F, sorry, equals to M dV per dt, okay? Okay, from this relation, this I here, where is I? Yeah, this I is BLV over R, okay? So we get, it should be like this, okay? And then, well, you get integral, somehow we get this one. You see that if, because there is no force, this applied force acting on this rod, so we have this terminal velocity is equal to 0. Terminal means that we take time t goes to infinity. Okay, so the rod at the end will be at rest. Okay. Is there any question? Any question? Any question? No. Okay, let us continue. So Lenz's law. So we have this circuit, okay, this rod and this conducting rod, and also there is resistance, okay. So if as we talked, discussed this previous example, okay, there is no applied force, so we have only have this V here. So this rod move to the right, okay, and below we have this rod moves to the left, okay. So we have this FB, this magnetic force induced by the changing of this magnetic flux. So the above picture is equivalent to say that we have a magnetic rod. We are moving towards this magnetic rod to the coil, okay? It means that in this picture, the magnetic flux increases, okay? Increases, why? Because the area that swapped by this rod becomes bigger, okay, than the previous. It is equivalent to say that we have a magnetic rod moves toward a coil, okay, then the flux become also increases, okay, become increasing, okay. So you see that the induced magnetic field becomes North Pole because it against the magnetic field of the rod. Okay, so that's why we have at the ring, the direction of the current is like this. Okay, because it produces magnetic field that repel the rod. Okay, somehow it repel the rod. So it should be north against the north, have the same pole. Okay, this induced electric field. This induced current or induced magnetic field. In this case, the second case, it means that the fluxes the flux is decreasing, okay, because the area swapped by this rod becomes smaller and smaller, okay. This picture equivalent to say that we move away this magnetic rod, move away from this coil, okay. And as I said last week, if this is the case, then the induced electric field somehow not repelling, but attracting the magnetic rod that has been moved away from the rod, from the ring, okay, from the ring. Somehow, this induced electric field, this induced current, electric current, will produce the magnetic field, the induced magnetic field that trying to attract this magnetic rod, okay? Because the magnetic flux is decreasing in this case. Is that, are you getting my point? Understand what I'm saying? Is there any question?
Yes, sir. Understand.
Understand, okay. Pictures tell everything, okay? That's why I prefer to make a problem with the picture. One picture tells everything. So we could also make the above example by, well, use this one, okay? So somehow we get a switch here, switch off and switch on, okay? This also has a the magnetic field also depend on time, okay? We switch off, on, off, on, off, on, okay? The magnetic field also depend on time, okay? It's varying with respect to the time, because the magnetic field, it depends on time, so it should be, we have the fluxes also depend on time, okay? Let's say this, let us keep this way. So in general, we could write this Faraday lens law. We have this integral, loop integral, E dot ds is minus dvb over dt. Okay, this is the changing of the change of flux, the flux change over time interval. Okay. Okay, so this is this example of long solenoid of radius capital R, has N turned wire per unit length, carries time varying current that varies equal to I max cos omega t. Okay, this I max is the maximum current. This omega is the angular frequency of the alternating current. Okay, we get this. Okay, so we get this integral, this closed integral A dot ds. Okay, this is equal to E times 2 PR. R is, okay, little r is the distance from the center of the solenoid to this point outside the solenoid, okay? So we get this one. this integral, this e to pi r, this fluxes is equal to b p r capital R squared. So you know that b in the solenoid, in ideal solenoid is, do you remember? This mu 0 times n times I, okay? Because I, it is depend on time, as you see from this one. So we have this b also depend on time. This implies that the flux also depend on time. So if we differentiate with respect to this time, we get this one is equal to e to pi r, okay? Then we get the induced electric field outside the solenoid is this one. Is there any question? Okay, if
Is
not,
this?
continue. Yes?
Oh, never mind, never mind. No, because I thought for a solenoid you divide by the length of the solenoid, or is that something else?
No, that's the magnetic field. What we
Oh,
compute here, this is the electric field. The induced electric field caused by the change of this magnetic field with respect to the time. So this is the part of integration we take this part of integration, the blue one, outside the solenoid.
oh, okay. So it's like many loops. Yep.
Yeah. But we only take one loop. With only, yeah. Okay. I mean, yeah. You could. Yeah. I mean, we took only one loop here because we have cylindrical symmetry in this case. So somehow this R here is not so far away. I mean, this R here is around the value of little r is around this capital R. Okay, it's not so far away. It's near the solenoid, around the solenoid, not very far away. Well, if it is very far away, when it is difficult to solve this equation, this Faraday's law, this Faraday lens law. Yeah, it's difficult. I mean, the easiest way is we take the example where this little r is around the solenoid. It means that this little r, the value of this little r is greater than capital R, but not so big, not so big. Almost capital R. Okay, is that clear? We preserve cylindrical symmetry in this case. Okay, we continue. Then we get this one, the induced electric field is this one, okay, for little r greater than capital R. So what about inside the solenoid? Okay, because inside the solenoid, the flux is P r little r squared times B. So this is the total fluxes. But if we consider only partial fluxes, it means that inside the solenoid, we have this flux, it's not longer this capital R, but we replace this capital R by little r, okay? This one. So we use similar as before, we take that this E times 2 pi r equals to minus P r squared dB over dt. Okay, using this formulation and this I formulation, we get that this E equals to this one. This E here is inside the solenoid, okay? Any question? If not, we continue. So the notion of this induction, the electromagnetic induction, it applies. We could apply the concept, this magnetic induction to have somehow these generators, to build a generators, electric generators. Somehow you could use this, for example, this loop here. This we have this external rotator, okay, and this rotates in the magnetic field, Then we get that this it will produce this induced electric field, electric current. Okay, will light up this line. Okay, so this is the potential difference here, or this EMF, EMF, electromotive force, that is produced by this generator. We call it AC generator. AC means alternating current, as we will discuss in the next section. Okay, so this is the concept here. So usually we get that we have this N turned wire, okay? This N here, so this phi B is equal to BA cos theta. Theta is the angle between normal direction of this area of this coil compared to the direction of this B, okay? We have this one. So theta is equal to omega times T, okay? We assume that omega is constant. So because we have N-turn wire, then the Faraday's law, we get this one. Okay. So as you see that the EMF that produced from the generator is also depend on time. Okay. So the sometimes zero. So from this graphics, okay, you see that the voltage that produced from this motor, AC motor, sometimes zero, positive at some interval of time, and then they become negative at several interval of time. Okay, so that's why it is called alternating current, because the pole is not really fixed. Okay, it alternates with respect to the time. Okay. Lady is outside the. Okay, that's the end of this induced electromagnetic induction. Let us move to the next section, which is the alternating current. Okay. Any question? Oh, sorry, this is inductance. Inductance. So inductance also. Okay. Let's say we discuss about inductance first. Any question? Okay, this picture shows that if you, for example, well, this device usually we oftenly see in the airport. Yeah, it detected if someone brings a metal. Okay. Yeah, the weakness is the metal. If someone brings, for example, a weapon from made from non-metal material, this device cannot detect such a weapon. If you have already watched the film, I think the title is about the Jackal, start by this Bruce Willis. So the Bruce Willis acts as a jackal. He built a weapon, a pistol from plastic. That's really interesting, that film. Okay, self-inductance. Okay, so in the last section, in the preceding section, we have we have considered this Faraday Lenz's law of induction. Okay, but in this section, we will discuss about Henry's law of induction. Okay, basically, well, these two pictures is basically equivalent. Okay, at the level of solenoid. Okay, at the level of solenoid. So if we consider a solenoid, there will be self-induced, we call it self-induced electromagnetic force of EMF. This self-induced EMF is proportional to the time rate of the change of the current. Okay, so the formulation is this one. Epsilon L is minus L di over dt. Okay. Okay, this equation 32.1 is the Henry's law. Okay, this one. But as you see that we get Faraday's law, Faraday-Lenz law from the preceding section. Yeah, so it should be equal. Okay, so this L here is called inductance. Inductance. It is a constant here. It is a constant. Okay. Inductance. The device called inductor. So the property is called resistance. The device is resistor. Capacitance, capacitor. Inductance, inductor. Okay. So this L here is constant. So if we equalize this 32.1 to the Faraday's-Lenz law in the preceding section, we will get this 30.2 equation. Yeah, we could express this L in terms of this N turn wire and then flux phi B over I. I is the current, induced current flows through this solenoid. So this formulation only valid if this I depend on time. What if we replace this I by a DC current? Cynthia Rida Larasati. Halo. Cynthia Rida. Cynthia Rida. No answer. Zahid Asmi Ibrahim. Halo. Zahid Asmi Ibrahim. Ahmad Risa Thohir. Ahmad Risa Thohir.
Hello, sir.
Hello.
Hello, sir. Can you hear me?
Okay. You should replace your name. Rename.
Oh, okay. Yeah, sorry, sir. It's from my UTS last week. Sorry, sir. I will replace my name.
Okay. So the question, can you ask? Can you answer my question? Siapa tadi? Who is it? Ahmad Rishad. Thohir.
Hello, sir.
Yeah. Can you answer my question? What
What's
if
the question?
I replace this I with the DC current?
Sorry, sir. Can you repeat?
You consider, you see this 32.1.
Yes.
Okay, what happened is I replace with this DC current.
Sorry, sir. I still don't understand, sir.
No, Reno. What happened?
I don't understand, sir.
You don't understand. Ahmad Rishad, you didn't rename. You still didn't rename your.
Yeah. When I was going to rename my name, you called me, sir. Sorry, sir. I will rename it now. I have renamed my name.
Bagas Irfan.
Yes, sir. Hello.
Yeah. What is your answer?
Will there not be induced electricity?
Sorry?
Will there no be induced electricity? Because it's a
Yeah.
different
Yeah,
current?
there is no induced EMF. Okay, yeah. Okay, thank you. Because the DC current is constant, okay? It doesn't depend on time. So di over dt is equal to 0, then we do not have this induced electric potential, voltage, induced voltage at the solenoid, in the solenoid. So it should be 0. Okay, so this I should be depend on time, okay? So this formulation, this 32.2, valid or holds only for time-dependent current. Okay. Okay, this L here, inductance, the units, the SI units is called Henry. 1 Henry equal 1 volt times S second over ampere. Okay. So
Hello,
let
sir.
us see why this L depends only on the geometry of this solenoid. Okay. Okay.
Sir,
Yes.
I think Nicholas. Oh, sorry, nggak jadi, sir. Ternyata udah masuk.
Okay. Yeah. Okay. Let us consider a solenoid, okay? Solenoid having an n turns and length L, okay? So you get from the preceding section, we get this B equals to mu 0 times n, capital N over L times I, okay? So the flux inside the solenoid, it should be B times A. Okay, this is equal to mu 0 and A over L times E. Okay, this 5E. So if you substitute this 32.2, okay, these fluxes, insert to this one, then we get this L, yeah, equals to mu 0 and squared A over L. Okay. This mu 0, it means that inside the solenoid, there is no additional material, okay? Okay, if mu 0, if there is additional material, for example, conducting materials such as metal, etc., or kind of metal, conducting metal, then this mu 0 is be replaced by mu. Okay, that's all, I think. So it means that the inductance, inductance of solenoids depend only the material inside the solenoid, which is represented by this mu 0, and the number of this turned wire, and squared the cross section or the area of the solenoid and the length of the solenoid. Okay. This this capital L, we have a specific name called self-inductance. This L, or inductance, just inductance, or for complete name is, the complete name is self-inductance. Any question about this aspect? If not, let us consider similar to the RL circuit. Okay, this RL circuit somehow, yeah, we get this DC electromagnetic force. This DC here, if this is ideal, yeah, the electric current is constant if we close the switch. Okay, in other words, the switch is on. Okay, but for example, if the switch, for example, is the initial condition, the initial phase or condition of the switch is open or off, okay, and then we close the switch, okay, then the current flows through this loop, okay. Then using this second Kirchhoff law, we get this one, okay. Epsilon is a constant. Why we have this one? Because at the interval, the short interval of time, this I in general depends on t. Okay. So if we solve this equation 32.6, we get that this I here is equal to epsilon over I equals to epsilon over R times this one 1 minus E 2 minus R T over L. Okay. This R over R over L, we call it tau. tau is the constant, time constant somehow. Okay, at t equals 0, yeah, this I here is the induced or transient, well, not transient, not transient, it's, is the current, the current that flows to this circuit, okay? At t equals 0, it will be 0, and then after a very, very long time, this I becomes a constant current, okay? And there is no induced electric field at the solenoid because the current is already constant. Is there any question? So the picture of this I here at t equals 0, it should be vanishes. It should be vanished, okay? And for t equal 1, t equal 2, and after a long time, it converts to this value, epsilon over r. What about the induced? The induced EMF, yeah. So it should be the case, decreasing with respect to the time. So if you take this time for a very long time, so this induced potential difference or induced EMF should vanish for a long time. Is there any question for this aspect? Any question? No question. Okay, let us continue. This is so it's similar to this RC circuit, yeah, this RL circuit. Okay, energy in the magnetic field, or energy in the inductor. Okay, so the energy of inside the inductor, the potential energy, is equal to this equation equal to a half times R I squared. Capital R, capital L, I squared. Okay. Excuse me. Salim?
I'll rename it.
Okay. Any question? No. So this is the potential and the potential energy inside the capacitor, inside the solenoid, or inside the inductor. So if we if we cast this, we can use this R here, this capital, the capital L here. Sorry, the capital L is equal to this one. This capital, where is it? I forgot. In the preceding section, I think, yeah. The preceding section, this L here, capital L, equals to this mu 0 and capital N squared A L, okay? This I equal to B mu 0 little n squared, then we get this one. This A times L is the volume of the solenoid or the volume of the inductor. Okay, if we divided this capital U over the volume, okay, then we get this one. This is the energy density per volume is stored in the capacitor, okay, in the inductor. Okay, this UB equals to B squared over 2 times mu 0. Okay, so this is general magnetic energy density. This 32.40. So then we also get about this mutual inductance. Okay, sample mutual, just a moment. Yeah. Just a moment, whether you have this. So mutual inductance, and it means that if we have two coils, yeah, we close, we take these two coils close to each other, okay? So like this. So somehow, if we have the current in the first coil, then it will induce, okay, induce the magnetic field on the second coil. But we have a condition here, okay? This I1 here, it should be depend on time, not constant, okay? If this is, we call it this M12. M12 mean this M is the notion of mutual inductance M12. It happens in coil 2 with respect to the coil 1. So it means that the induction, this M12, is in the second coil or coil 2, yeah, this mutual inductance, caused by this from the coil 1, yeah, this N1 and I1. Okay? So it should be this M12 is equal to, we have this N2 times V12 over I1. Okay, so this is the induced E2, yeah, at the second coil. Yeah. This epsilon 2 is equal to minus N2 times d phi 1 2 dt. So d phi 1 2, yeah, is equal to this M12 times I1. Okay? So in the epsilon 1 2 here, sorry, this epsilon 1, we get this minus M21. So it should be at the coil 1 with respect to the coil 2. So we get this Faraday's law equation like this 32.70. So because this interaction between these two coils is ideal, it means the ideal means that there is no power loss, okay? There is no power loss. So it means that the power ideally transferred to the second coil. There is no power loss. If there is no power loss, we could say that this M12 is equal to M21. Okay, the efficiency is 100%. If this is the case, then we get and if this is the case, yeah, then we get this epsilon. Then we get this epsilon 2 equal to minus m di1 per dt, and epsilon 1 is minus m di2 over dt. And we could also, there is, well, there is a relation between this epsilon 2 and epsilon 1. Any question about this mutual inductance? If not, we continue.
Pak,
Ya,
tadi kenapa nggak ada power loss pas ditransfer gitu, Pak? Kenapa nggak ada power loss tadi?
yeah, this ideal, the interaction is ideal. It means that there is no energy loss. So so in general, if we, for example, we have a coil that induce the second coil, it should be there is a power loss. In general, the resulting induced electric field, well, the mutual is not the same. So if the mutual is not the same, so there is no relation between this epsilon 2 and epsilon 1. If there is no, if this is not ideal, so it should be, for example, this m. So for example, in epsilon 2, yeah, in the second coil, yeah, it would be this. Let me explain in the. Okay. Okay. Okay, you can see the whiteboard, yeah. So we have this coil 1, and let's say this is N2, yeah, I2. Okay. If sorry, this epsilon 2 is minus M12 DIR. Okay, so we get the induced epsilon 2. This is at the coil 2, yeah. This induced electric voltage, EMF, epsilon 2, is caused by the change of I1 with respect to the time, okay? This M12 is the mutual inductance at coil 2 caused by coil 1. That is from the statement here, M12, okay? So let's say at the beginning, we get this relation. Okay? So because epsilon 2 also depend on time, so this induced I2 here depend also on time. So it will also induce the first coil. So the first coil, this induced epsilon 1 is minus M, this one, I2 over dt. Okay? So if the interaction is not ideal, it means that M12 is not the same as M21. So usually this M12 is, let's say, M21. This eta is called efficiency. Maybe this is the correct one, the efficiency. The efficiency, it's less than or equal to 100%. Of course, this is equal to zero. Okay. If it's not an ideal, this should be like this. Though it equivalent to say that for eta, if eta is 1 or 100%, there is no energy or power loss at both sides. This is ideal. Okay, is that clear?
Yes.
Okay. Let's begin.
Thank you,
Okay,
sir.
let's continue to the book. Let's get back. Okay. So this is ideal condition. So somehow this epsilon 2 and epsilon 1 is also related. Yeah. Okay, I should skip this one. Okay, oscillation in LC circuit. Okay. So, wait a moment. Oscillation. Okay, I think it's outside SAP, yeah? Outside the content of SAP. Okay, if there is no question, let us continue to alternating current directly AC circuit. Okay. Okay, for the source, for example, we have this source, okay, this voltage, yeah, this for AC EMF. You see that this voltage depends on time, so this time varying voltage, okay. For example, we have this form, this sinusoidal, Vmax sinus omega t. So where omega t is the angular frequency of the AC voltage. Okay. The symbol of the AC source is this, like this. Okay. Because we do not distinguish, yeah, between the pole. The pole is alternating. Alternating means that sometimes zero, sometimes positive, sometimes negative. Okay, let's say if we connect this AC source, the AC source with the resistor. Okay, like this. As you see that if this voltage is, the form of voltage is sinus omega t, where omega is a constant, the angular frequency, we get that the potential difference of the capacitors, this delta VR, is equal to delta Vmax sin omega t. Okay, so it should be IR, it should be delta VR over R. Okay. So we have here the current that flows through the resistor is equal to I max sin omega t. If we compare this 32.2, which is the flow, the currents flow through this resistor, and the voltage, the source voltage, this phi max sin omega t, they have the same phase, okay? Okay, they have the same phase. So if we draw, for example, this IR against delta V, okay, then we get this picture. Okay, so let's say what we call it. This is called phasor diagram. The phasor diagram. So this one is omega t. You could also in phasor diagrams, you could also draw something like this. For example, this, for example, IR, B, for example, and this one is omega t. So this is, for example, IR, and this is V. Okay, that's an alternative picture of phase diagram. Phasor diagram. Phasor diagram. Okay. Okay, so they have the same phase, so said to be in phase. In phase. Any question about this R circuit, this resistor circuit? No, I think it's the easiest one. Okay, what about if we consider we will come back or we will discuss it. Okay, about this power, the power in the R circuit. Yeah. As you see that because this I here is depend on time, so in this case, the power we have only consider the average of the power. Yes, okay. So this average here is I squared RMS squared times R, okay. This is RMS mean root mean square. Root mean square is EI squared average and square root. Root mean square. You have to average and then square root, quadratic. This one. What about the inductor in an RC circuit. So if we consider, for example, this L, the inductor, we have the potential difference is delta VL, okay? Delta VL is equal to L di over dt, okay? So in this case, we get that because the delta VL is equal to delta V, so it should be L di per dt equals to delta Vmax sin omega t. So if you integral, you will get the current that flows at the inductor, okay? Then we get this 33.7. So you see that the current in the picture, they have phase difference, phase difference 90 degrees, 90 degrees, okay? So somehow if, so it said that the currents lags behind the voltage by 90 degrees, okay? So for example, at t equal to 0, we have 0 potential, but in the current we get this minus, okay? So the current is lagged behind. Okay, by 90 degrees. So it means that in the phasor diagram, the factor potential is perpendicular to this, let's say, the factor of current, okay? This picture. Any question about this? So it should be IL, if we rewrite in terms of sinus, it should be delta mx over omega L times sin omega t minus p over 2. Okay, the quantity here, omega L, we call it inductive reactance, XL. Not extra large, XL, inductive reactance. XL, defined as omega times L. Okay? Any question about this? Okay. Let's stop here. I will summarize today's lecture in bahasa, okay? Oke, jadi kita balik lagi sekilas, udah 2 bab ya. 2 bab, hampir 2 bab lah ya, karena terakhir itu. Oke, jadi kita bahas pertama-tama itu tentang hukum Faraday. Not ampere. Hukum Faraday yang mengatakan bahwa perubahan Okay, this one. Jadi yang mengatakan bahwa perubahan flux magnetik itu dapat menyebabkan adanya medan listrik induksi atau beda potensial ya, induksi. Jadi bisa dikatakan dia sebagai sumber tegangan induksi. Nah, seperti ini contohnya. Jadi ininya seperti ini biasa kita tarik ya gitu ya. Nah, kita tarik itu akan ada perlawanan seperti perlawanan dalam tanda kutip ya. Apa namanya gaya FB ini apa? Gaya magnetik akibat medan listrik induksi ya. Karena perubahan flux ya, fluxnya makin naik. Kalau fluxnya makin naik itu cenderung melawan. Nah, makanya ini nanti akan ada perlawanan di sini. Gitu. Nah, karena nanti akan ada keseimbangan antara apa namanya gaya yang kita tarik dengan FB, di mana gaya FB di sini F-up maaf itu kita ambil itu adalah sama dengan sama dengan FB maaf F-up. Kalau yang di sini tuh gambaran mikroskopiknya antara medan listrik induksi ya FE di sini dengan FB di sini ya. Jadi dia seimbang itu didapatkan kecepatan terminalnya itu akan sama dengan E sama dengan VB. Oke, karena kenapa kecepatan terminal? Karena B-nya ini diambil konstan kan ya. Kalau B-nya diambil konstan, maka akan didapatkan bahwa V di sini secara umum itu bergantung pada waktu. Ya, V di sini itu bergantung pada waktu, tapi lama-kelamaan dia akan seimbang. Oke, nah seimbang itu adalah dia memenuhi ini. Persamaan ini yang saya ingkari. Jadi dapat E sama dengan V kali B. Oke. Nah, secara makroskopik itu dikatakan bahwa beda potensial di batang ini itu adalah E kali L gitu ya. Karena kan di sini ada muatan positif yang ke atas ya. E kali L gitu ya. Nah, E kali L di sini itu sama dengan apa namanya? Ini adalah beda potensial, ini adalah BLV, ini adalah perubahan flux magnetik per waktu. Itu didapatkan seperti ini. Jadi ini sebenarnya dengan ini ekuivalen, sama. Jadi gambar di sini itu ekuivalen dengan saya katakan bahwa saya punya sumber arus induksi, yaitu sebenarnya tidak tepat DC ya. Seharusnya itu lebih tepatnya DC ya DC tapi yang bukan konstan arusnya. Karena arus ini bisa berubah-ubah ya arah dan besar arusnya gitu. Seperti itu. Nah ini jadi gambarannya itu didapatkan bahwa arus yang mengalir dalam rangkaian tersebut itu adalah BLV dibagi R. Nah, daya yang bekerja pada apa namanya batang ya, karena di situ ada gaya, di situ gaya yang bekerja F-up namanya applied force. Dan kebetulan applied force di sini tuh sama dengan gaya magnetiknya ILB yang FB tadi. Halo? Halo?
Halo Pak.
Tadi terputus ya?
Iya, keputus tadi.
Sorry. Udah ngomong capek-capek. Oke, kita sampai sini kan tadi ya. Jadi kita dapatkan, karena F-up di sini sama dengan FB itu sama dengan ILB. Oke, jadi didapatkan ini adalah epsilon kuadrat dibagi R. Ini adalah daya yang bekerja pada rangkaian ini. Jadi batang ini sebagai dia ideal dianggap sebagai sumber tegangan listrik induksi. Kemudian jadi kita tadi bahas juga tentang apa namanya induksi GGL atau EMF yang bekerja pada batang yang diputar dengan kecepatan dengan kecepatan sudut konstan ya. Jadi kecepatan sudut konstan itu didapat bahwa DE itu adalah BV kali DR gitu ya. Di mana ya DR di sini adalah infinitesimal dari batang ini. Oke, ambil V-nya ke sana. Infinitesimal. Jadi didapat V di sini pada yang ini itu adalah omega kali R. Oke, sehingga didapat kalau saya integrasikan integralnya itu dari 0 sampai L gitu kan berapa setengah B omega L kuadrat. Ini juga sama kalau misalkan saya mengambil medan magnetik ya. Ini aja medan magnetik aja, tidak ada gaya yang bekerja, tidak ditarik ya. Karena dia itu awal dengan kecepatan awal VI yang konstan ya. Tidak ada gaya luar selain FB di sini, maka kalau kita lihat ya dari sini rumusan ini, maka lama-kelamaan kecepatan itu akan menuju 0 kan ya, akan diam. Jadi kalau lama-kelamaan batang ini akan diam. Jadi terlihat dari sininya. Kemudian ada hukum Lenz ya. Jadi kalau kita lihat di sini yang gambar pertama ya. Kalau gambar pertama ini fluxnya ini itu dia makin besar. Flux makin besar itu cenderungnya melawan gaya medan magnetik induksi yang dihasilkan ini seperti ini. Ekivalen dengan batang didekatkan, dan batang didekatkan itu fluxnya makin besar. Sehingga dia kecenderungan akan melawan. Nah itu ekivalen dengan gambar A ini. Yang gambar yang A yang di sini. Sedangkan gambar B di sini ketika dianya itu makin kecil fluxnya karena kecepatan batangnya itu ke kiri, dia ekivalen dengan gambaran bahwa batang magnetik itu menjauh dari kumparan. Sehingga kumparan itu kecenderungannya akan menarik batang magnetik, artinya bahwa medan magnetik yang dihasilkan ini akan menghasilkan ini kalau ini north utara, ini selatan south. Jadi seperti itu gambarannya. Kemudian kita langsung pada ini ya. Jadi ini Anda bisa baca sendiri ya terkait dengan medan listrik induksi pada solenoid. Oke, biar supaya mempercepat waktu. Nah, ada satu lagi juga yang terkait dengan kalau ini kita bicara tentang hukum Faraday-Lenz, yang berikutnya ini adalah kita membahas tentang hukum Henry. Kalau tadi itu adalah hukum Faraday-Lenz itu memperhitungkan medan atau tegangan induksi yang dihasilkan itu akibat perubahan flux magnetik. Nah, kalau sebentar. Kalau yang di sini itu kita mengenalnya yang disebut adalah hukum Henry ya. Jadi hukum Henry itu terkait dengan induktansi diri atau induksi diri ya dari sebuah solenoid yang kita sebut ini adalah induktor. Jadi ini adalah hukum Henry. Hukum Henry itu adalah gaya induksi yang dihasilkan pada sebuah solenoid itu bergantung pada perubahan arus yang dihasilkan. Jadi epsilon L di sini itu adalah GGL induksi. Oke. Nah, karena L di sini adalah konstan ya. Konstan dan di sini disebut adalah induktansi dari coil atau solenoid. Nah, kalau kita samakan dengan hukum Faraday-Lenz ini, itu akan saya dapatkan ternyata L di sini sama dengan NVB dibagi I. Oke. Dan kalau kita ini kan, kalau kita apa namanya gabungkan dengan rumus-rumus sebelumnya seperti ini kan, ini adalah rumus dari medan magnetik dalam solenoid. Ya kan? Ini fluxnya. Oke, kalau saya masukkan ke sini, itu akan saya dapatkan ternyata L di situ adalah sama dengan mu 0 N kuadrat A dibagi L. Oke, mu 0 itu menggambarkan apa namanya, benda apa atau bahan apa yang dimasukkan ke dalam solenoid. Kalau dia itu vakum, itu adalah mu 0. Kalau bahan ferromagnetik atau bahan diamagnetik atau paramagnetik, itu kita menggantinya dengan mu gitu ya. Jadi ada bahan mu 0 di sini biasanya untuk yang vakum. Sedangkan N besar itu adalah jumlah linitan, A itu di sini adalah area atau luas dari apa namanya, dari solenoid, yaitu terkait dengan ini tutup, luas lingkaran. Kemudian yang L kecilnya itu adalah panjang solenoid. Jadi memang induktansi diri itu bergantung pada geometri dari solenoidnya. Oke. Kemudian di sini kita juga bahas tentang RL circuit. Jadi RL circuit itu seperti RC circuit. Ya. Jadi kalau awalnya saklar dibuka, kemudian ditutup gitu ya. Ini karena ada yang disebut namanya dalam tanda kutip arus transient. Soalnya kalau arus transient itu kan sebenarnya dia meluru. Kalau dia ini arusnya itu cenderung tetap gitu. Jadi ya transientnya maksudnya saya bilang dalam tanda kutip. Jadi kalau ini nanti kita pecahkan persamaan 32.6 ini, itu akan saya dapatkan bahwa bentuk arusnya itu di persamaan 3.27 solusinya. Nah, di mana tau itu adalah disebut konstanta waktu yang sama dengan R per L gitu ya. Nah ini kalau kita lihat, kalau T-nya menuju tak berhingga atau waktu yang sangat lama, I di sini akan kecenderungan tetap gitu kan, menjadi konstan gitu. Makanya suku yang ini itu yang dikatakan transiennya itu akan hilang, akan nol. Jadi makanya kalau yang di sini itu gambarnya adalah gambar arus tadi ya. Jadi arusnya itu cenderung tetap, yang suku transiennya ini adalah menjadi nol gitu ya, sehingga tetap. Nah, arus induksinya Anda lihat, arus induksi kan terkait dengan perubahan dari per dt. Kalau I-nya udah lama-lama konstan, GGL induksinya lama-kelamaan akan nol. Seperti itu. Nah ini contoh aja kalau dia itu ada sebentar. Ini kan harus ada R kan ya, betul. Itu yang apa namanya untuk RL ya. Kemudian ini energi pada induktor. Nah energi pada induktor itu ada lihat di 32.12 ya. Itu adalah setengah LI kuadrat. Oke. Jadi kalau Anda masukkan L itu apa, dengan I, L itu adalah ini, dengan I itu adalah ini, B per mu 0 dibagi N kecil gitu ya. Itu kan Anda dapatkan di sini, U besar itu sama dengan B kuadrat per 2 mu 0 kali AL, dan AL itu di sini kita tahu adalah volume dari solenoid. Jadi kalau saya bagi dengan volumenya kali AL, itu akan saya dapatkan U kecil B itu adalah rapat energi per volume, rapat medan magnetik per volume yang disimpan dalam induktor itu adalah UB sama dengan B kuadrat dibagi 2 mu 0. Walaupun saya turunkan ini dengan solenoid ideal, tapi secara umum rumus ini berlaku ya. Sama halnya juga dengan kalau yang listrik tinggal diganti E kuadrat aja, setengah epsilon 0 E kuadrat. Yang apa? Rapat energi listrik ya per volume. Ini saya. Kemudian ini juga saya membahas tentang induktansi bersama mutual ya gitu. Jadi awalnya misalkan saya punya coil 1, ini coil 2, coil satunya itu adalah yang berubah terhadap waktu ya, sehingga menyebabkan adanya arus induksi di coil kedua. Nah itu makanya di sini nanti akan ada yang disebut namanya mutual inductance M12 saya ambil. Jadi M12 itu adalah induksi bersama pada coil kedua akibat akibat coil pertama. Gitu. Jadi M12 itu sama dengan N2 V12 per I1. Sedangkan M21 di belakangnya 1, berarti itu adalah coilnya yang pertama akibat kedua. Itu berarti M21 sama dengan N1 V21 per I2. Karena akibat I2. Oke. Nah, jadi secara umum epsilon 2 itu adalah sama dengan minus M12 kali DI D1 per DT. Sedangkan I1 itu adalah M21 kali DI2 per DT. Nah, seperti tadi saya bilang bahwa kalau dia itu interaksinya ideal, artinya tidak ada energi yang hilang atau daya yang hilang, maka M1 dan M2 ini bisa diambil sama. Ya, maka yang disebut di sini adalah M di sini adalah induksi bersama. Kalau dia itu tidak ideal, itu berarti seperti tadi. Jadi M12 itu bisa jadi sama dengan suatu konstanta eta yang disebut efisiensi dikali dengan M21 atau M12 ya, kebalikan. Jadi artinya nanti di sini tidak sama dengan M gitu. Jadi itu yang tidak ideal. Tapi pada umum kita membahas yang ideal. Nah, yang ini semuanya di luar SAP ya, jadi yang nggak akan diujikan. Jadi ya kalau Anda tertarik membaca sendiri silahkan gitu ya. Jadi kita kembali ke apa namanya tadi sirkuit apa rangkaian AC gitu ya. Rangkaian AC. Jadi AC itu secara umum alternating current ya. Sebenarnya kurang tepat juga kalau kita bilang harus bolak-balik. Maksudnya itu harus berubah-ubah. Berubah-ubah apanya? Kutubnya tidak selalu tetap. Kadang 0, negatif, dan positif. Nah, delta V ini di sini secara umum sederhananya kita ambil dia bentuknya sinus omega T. Dan omega ini di sini konstan. Oke, dan omega itu disebut namanya frekuensi sudut. 2πf sama dengan 2pi per T. Ini gambarnya ya. Kemudian tadi juga kita bahas tentang resistor gitu ya. Resistor itu seperti ini ya. Ini sumber tegangan AC-nya. Didapatkan bahwa ternyata harusnya mengalir pada resistor itu sebenarnya Imax kali sin omega T, artinya dia itu sefasa gitu ya. Sefasa. Jadi dia seperti ini. Nah, gambar ininya itu seperti ini. Gitu. Kemudian untuk yang ada induktornya, ini ada ini. Karena dia itu I-nya itu bergantung pada waktu atau tidak konstan, biasanya yang kita ambil itu yang diukur di voltmeter atau ampermeter itu yang average-nya. Sebenarnya kalau voltmeter itu VRMS, kalau ampermeter itu yang IRMS-nya. Jadi kalau yang P average ya itu adalah daya yang hilang pada rangkaian kapasitor itu adalah I RMS kuadrat kali R ya. Nanti kalau Anda masukkan adalah setengah I kuadrat max, I max kuadrat kali R. Oke. Kemudian induktor ya, ada satu lagi induktor dalam rangkaian AC. Ini persamaannya kalau kita hitung dia ternyata akan tertinggal gitu, tertinggal 90 derajat. Sehingga gambarnya itu seperti ini. Jadi kalau tertinggal itu yang potensialnya 0, ininya negatif. Atau dengan kata lain, potensialnya udah ada, dia masih 0 gitu ya. Namanya tertinggal kan gitu. Jadi apa istilahnya kita udah nyampe, orang belum kan. Yang orangnya itu yang tertinggal. Kita lebih dulu gitu. Nah, jadi rumusannya itu IL ini yang mengalir pada induktor itu seperti ini. Maksimum delta V maksimum dari omega L sin omega T kurang pi omega kurang pi per 2. Kemudian kalau yang gambar fasornya seperti ini tegak lurus kan antara I delta V dengan IL. Nah, kemudian omega L itu disebut namanya reaktansi induktif ya, gitu artinya memang ini ada ketika omega ada. Ya. Jadi apa istilahnya ini dikatakan reaktans induktif karena ya tadi apa dari sumber AC. Gitu. Kalau bukan dari sumber AC tidak akan mungkin ada. Mungkin itu aja dari saya. Terima kasih. Udah lebih 8 menit ya. Anda silakan istirahat. Jam 2 kan Anda kuliah lagi. Terima kasih semua. Selamat siang. Jaga kesehatan, jangan lupa.